Hello, I'm Rana Spiritu, and I work with the members on the screen to complete the fourth design assignment of the semester. The task of our assignment is to maximize the transverse tip displacement by placing an electric field and temperature change over a piezoelectric polymer bimorph cantilever. We were free to manipulate the thickness of the polymer as well as whether it was on the top or the bottom. The width, length, piezoelectric coupling matrices, thermal coefficients, compliance matrices, and permittivity matrices were all given and as seen on screen. Along the way, we uncover how the material parameters play into induced curvature and how axis systems completely change our answers. I'm mainly focused on building of the Maple and the Flex PDE simulations. We simulate the strain produced by piezoelectric strain to be the product of piezoelectric coupling matrix and the electric field. The piezoelectric strain is the result of asymmetry of atoms and charge within a material and allows us to induce charge restraint by placing two layers on top of each other. We simulate the thermal strain, thermal expansion, to be the product of the thermal coefficient and the change in temperature. Thermal expansion works because changing the temperature changes the vibration of atoms of that material, and in order to release energy, the material will want to expand. Curvature is caused when we have two different layers expanding at different rates. This difference entices the material to bend in order to release energy. With the nature of our constraints, we can measure that we'd prefer to have Z as the thickness, Y as the width, and X as the length. The piezoelectric strain dictates that a Z-directed field would produce the largest longitudinal strain, so we aim to set our code with this axis system in mind. Before building a flex code, we use Maple using our knowledge of beam bending to allow us to create code that will let us verify our flex later on. Our flex code was built by first rotating the flex PDE axis system to allow us to extrude in the Y direction rather than the Z. It makes building in flex easier as opposed to rotating our given matrices. From here, we defined our geometric boundaries and the parameters associated with them. We use these differential equations, which explain that the partial derivative of axial and shear stress are equal to the total displacement in that direction. In order to find these stresses, we use Hooke's law and our understanding that mechanical stress is equal to the total stress minus thermal stress and piezoelectric stress to build all the strain contributions into our flex code. One limitation, however, is within n-grid errors. So we built it in 2D as well by omitting the width direction component to bypass this limit. We also did several tests. We checked to see if the system bends in the direction of the piezoelectric due to the polymer expanding faster when under thermal strain only, which it does. We check to see if the system bends to the piezoelectric under only voltage, since it would shrink under an electric field, which it does. We check to see if the curvature is 0 with no polymer, since curvature is caused by a difference in strains, which it also does. And most importantly, we check to verify that the polymer's position doesn't change the magnitude of curvature. This is the case, and it makes sense because the individual layers will react independently to the stresses. The direction of strains do not change among the layers, but the curvature will have to switch directions as in this picture. With this knowledge, we only need to run one Python with either the polymer on top or the polymer on the bottom, and it will not make a difference in our final displacement. Like previous DAs, we use string manipulation and a grid search with our given range and a close step size to zoom in into a scatter plot until we can precisely pick out an extrema. To optimize, we use linear interpolation to eliminate noise through parabolic interpolation and to find points closer to our accurate extremas. This plot here plots points in comparison to a curve-fitted plot produced by our linear interpolation. We also used a gradient descent as another method to calculate when the change of slopes is 0, and holding this to be our maxima or our minima. And given the constraints, the maximum displacement is 677 nanometers at a polymer thickness of 565 micrometers. And this makes sense because the calculations explain that given our constraints, piezoelectricity will have a higher impact on our curvature. Having a polymer with too much thickness increases its compressive strength, inhibiting its curvature, while having too thin doesn't oppose strain enough to cause curvature.